You know, we often talk about the Internet of Things. Well, like it's this futuristic convenience layer, right?
The smart fridge ordering milk.
Exactly, or your thermostat knowing when you're home, but that's just the consumer surface level.
Right, that's just the tip of the iceberg.
The real Internet of Things, the industrial backbone, that is a completely different beast. We are talking about autonomous vehicle grids, remote robotic surgery.
Mm-hmm. And supply chains tracking millions of assets in real time.
And when you get to that level, you're not just dealing with convenience.
No, you're dealing with critical infrastructure.
Yeah.
And the biggest headache in that space right now is, well, it's a paradox.
The paradox.
We need these systems to be incredibly secure, which, usually means using blockchain, but we also need them to be incredibly fast.
And historically, those two things, blockchain security and real-time speed, they've been mutually exclusive. It's the classic trilemma.
It is. If you want decentralization and security, you usually sacrifice scalability and speed.
But there's a new study out of Chiba University in Japan, published just last month in IE Transactions on Network and Service Management, that suggests we might be able to cheat that trade-off.
It's a fascinating piece of research. They're proposing a new algorithm called Dual Perigee.
Dual Perigee.
And the claim is bold. They've managed to cut blockchain network delays by nearly half.
Half.
48.54% to be exact, and without upgrading a single piece of hardware.
Wow, which implies the problem wasn't the hardware to begin with.
Exactly.
The problem was the way the devices were talking to each other.
The connections themselves.
So for this deep dive, we are going to unpack this dual perigee algorithm. We need to understand why this thing called network topology is the silent killer of IoT performance.
Mm-hmm. And how this new approach fixes the gossip protocol problem.
And ultimately what happens when we remove all that digital friction from a fully connected world.
It really comes down to the architecture of how information moves. And to understand the solution, we first have to understand why putting blockchain on IoT devices has been, well, kind of a disaster up until now.
Well, it's the nature of the environment, isn't it? In a standard blockchain setup, like a Bitcoin or Ethereum mining rig, you have these powerful computers plugged into the wall.
High-speed fiber connections.
Right. But in IoT, you are dealing with resource-constrained devices, sensors running on batteries, mobile chips in cars. They don't have infinite bandwidth.
Precisely. And yet, standard blockchain protocols treat them like they do. Most blockchains use what we call unstructured overlays.
Relying on gossip protocol.
Exactly.
Okay, let's clarify gossip protocol for everyone, because it sounds informal, but it's a specific technical term.
It is.
It basically means that when a node receives a piece of data, say a transaction, it just randomly selects a few of its peers.
And passes it on.
And then those peers pick random peers and so on. It spreads like a rumor.
Right. And the unstructured part means there's no map. A device doesn't necessarily know which peer is the fastest or the closest. It just picks.
It picks randomly from whoever it's connected to.
Now, in a robust network with unlimited power, that's actually great. It's hard to censor. It's very resilient. But in an IoT network,
it's incredibly inefficient.
A total mess.
Because of that duplicate data issue. The source material highlights this pretty heavily.
Oh, yeah.
So if I am a sensor on a bridge and I use a gossip protocol to broadcast a structural warning, I'm sending that data to my neighbors. But my neighbors are also sending it back to me.
And to each other.
And to each other. So you get this echo.
And suddenly, your very limited bandwidth is completely saturated with echoes. You are receiving the same message 5, 10, maybe 20 times.
That creates congestion.
Huge congestion. The study points out that this redundancy causes long queues in the memory pool. The network becomes so busy processing duplicates that new critical information gets stuck in traffic.
It's so interesting because usually in computer science, redundancy is a safety feature.
Right, you want backups.
But here, it's a bottleneck. The researchers explicitly state that the lag isn't due to the encryption math being too hard, it's due to inefficient data sharing.
Caused by this random topology.
Right.
And that is the key insight. The topology, the shape of who is connected to whom, is messy. It's a tangle.
Okay.
And that brings us to the innovation from Associate Professor Keen Nguyen and his team. They realized that if you want speed, you can't rely on random connections. You need the network to organize itself intelligently.
Enter dual perigee. Now, perigee, that's an astronomical term.
Right. It's the point in an orbit where a satellite is closest to the planet.
So the name implies finding the closest or maybe the best connection?
Exactly.
But what about the dual part? That's what makes a specific algorithm so different from previous attempts, right?
Yes, and this is where we get into the mechanics. Previous optimization algorithms might have looked at a single metric, usually just latency or ping.
So basically, how fast did you answer me?
Yeah, that's it. But the team at Chiba University realized that in a blockchain, not all data is the same size,
Okay, so you have transactions,
which are small individual records,
and then you have blocks.
which are bundles of mini transactions. They're much, much heavier data packets.
Ah, I see where this is going. A connection that is good at passing small notes.
Might be terrible at handing over a heavy box.
So if you only optimize for one, you might end up choking the other.
You're absolutely right. And that's what Dual Perigee solves. It evaluates neighbors on both fronts simultaneously.
How does it do that?
It creates a scoring system. Each device on the network acts as its own independent agent. It monitors the peers it's connected to.
Okay.
And it asks two questions. How fast is peer A delivering transactions? And how fast is peer A delivering full blocks?
Yeah.
It combines those two metrics into a weighted score.
And if that score drops below a certain threshold, what happens?
The device initiates a neighbor churn.
A neighbor churn.
It disconnects from the underperforming peer and randomly selects a new one from the network to test out.
I love that term, neighbor churn. It sounds polite, but it's actually pretty ruthless.
It is ruthless.
The device is constantly firing its slowest friends and hiring new ones to see if they're faster.
But it results in a self-optimizing topology. Over time, that randomness just disappears.
So the network naturally rearranges itself.
It rearranges so that devices are connected to the peers that provide the absolute best performance for their specific location and hardware.
Now, there is a crucial detail here that we need to mention. The source material emphasizes this has to be done via passive measurement.
Yes, this is vital for the things in Internet of Things. If you're doing active measurement, you're constantly sending out ping requests.
So you're basically asking, are you there? How fast are you? Over and over again.
Right, which eats up bandwidth and, more importantly, battery life.
Right. If you're a remote sensor somewhere, you can't afford to waste energy just pinging your neighbors every second.
Exactly. Passive measurement means the device doesn't send extra signals. It simply watches the traffic that is already flowing.
Oh, that's clever.
It times how long it takes for a message to arrive compared to when it was created. It's analyzing the flow without adding to it.
It's like judging the traffic speed by watching the cars go by, rather than driving a test car into the mix yourself.
That's a perfect analogy. And this is what keeps the algorithm lightweight, which is a requirement for these low-power devices.
So on paper, this sounds solid. You've got a decentralized dual-metric passive measurement system. But the team didn't just theorize this,
No, they ran a simulation using the NS3 network simulator.
which is the industry standard for this kind of modeling.
It is. They set up a 50-node network simulation to mimic a congested IoT environment. And the comparisons were, well, they were stark.
They compared it against two things, right? The standard Ethereum protocol
The gossip protocol.
and the original Perigee algorithm, which was a single metric optimization.
And the comparison against Ethereum is the headline grabber. Dual Perigee reduced the block propagation delay. That's the time it takes for a block to spread through the whole network by 48.54%.
Cutting latency in half is massive. But I found the comparison to the original Perigee even more telling.
Oh, yeah.
The original was already an optimized system, but Dual Perigee beat it by over 23%.
And that 23% is the dual factor at work. It proves that distinguishing between transaction speed and block speed really matters.
How so?
The original Perigee likely optimized for general connection speed, but maybe kept peers that were fast at small packets but choked on the large blocks. Dual Perigee filters those out.
And Dr. Nguyen's commentary on this was quite optimistic. He said this bridges the gap between theoretical design and practical deployment. Because until you solve this latency issue, secure IoT is just a nice idea that doesn't work in the real world.
And that brings us to the so what of this whole thing. Why does it matter if a network of 50 nodes saves a few hundred milliseconds?
It matters because of what those nodes represent.
Exactly. The study uses the term mission critical. We aren't talking about your toaster.
No, we're talking about smart cities and healthcare.
Take the healthcare example.
Yeah.
Imagine a remote monitoring system for high-risk patients. These devices need to log vitals securely on a blockchain so the data is immutable and private.
Okay, sure.
But if a patient goes into cardiac arrest, that alert is a transaction that needs to get to the hospital's node instantly.
In a gossip-based network, that alert might get stuck in a queue behind a bunch of redundant data packets.
It could, yeah. But in a dual perigee network, the device has already optimized its path to the hospital.
So the message gets through.
The difference between 500 milliseconds and 2 seconds can be life or death in that scenario.
Wow.
Or look at autonomous traffic grids.
Right. If you have cars negotiating right-of-way at an intersection, they're essentially creating a temporary little blockchain of agreements. I go first, you go second.
Right. And if the latency is too high, the cars can't agree in time. They have to stop.
Or worse, they crash.
Or worse, they crash. By reducing that delay by nearly 50%, you move from a theoretical system to one that can actually handle traffic at 60 miles per hour.
So it effectively removes the speed bumps from the digital road. It allows the infrastructure to think as fast as the physical world moves.
And that is the dream of the fully connected digital infrastructure that the researchers talk about. A world where the digital ledger is perfectly synced with physical reality.
However, and we have to pivot here, because we can't talk about perfect tracking and perfect syncing without talking about the implications.
You're referring to the feedback from the listener, Rob, on the source article.
Yeah. Rob left a comment that was pretty blunt. He just asked, has anyone ever thought that we don't need such surveillance technology?
And it's a valid critique. We tend to frame efficiency as this absolute good.
Faster is always better, right?
Faster is always better. But in the context of data collection, friction is sometimes a form of privacy.
Oh, that's a really interesting way to put that. Friction is privacy. So you mean the fact that it was slow was actually protecting us?
In a way, yes. Think about it. If a network is congested, if it's prone to duplicate data and long queues, it is very difficult to conduct mass, real-time surveillance. The system simply can't handle the bandwidth of tracking every car, every sensor, and every person simultaneously.
It breaks under the load.
It breaks.
But dual perigee, it fixes the load. By optimizing the topology and removing the redundancy, it frees up all that bandwidth.
Correct. It creates a streamlined pipe. If you have a network of autonomous vehicles using this algorithm, the location data of every single car can be logged, verified, and stored on the blockchain instantly without clogging the system.
And because it's blockchain, that data is immutable. It's not a log file on a server that gets deleted after 30 days.
It's a permanent record of movement.
So Rob's point is the other side of the coin, the same technology that ensures an ambulance gets a green light instantly.
Also ensures that there is a permanent, searchable record of exactly where that ambulance and everyone else was at any given second.
The researchers, of course, are engineers. Their mandate is to solve the technical bottleneck, and they did that brilliantly. Dual perigee is an elegant piece of math.
But the implementation of it brings us into that gray area.
It's the dual-use nature of all high-performance tech.
It is. The researchers envision trustworthy digital infrastructures. Trustworthy usually means it works when I need it to. But to a privacy advocate, trustworthy might mean it keeps my secrets.
And those two definitions are clashing here.
They are.
And it's interesting that the solution is decentralized. There is no big brother central server directing the surveillance in this model.
No, the network itself is the watcher.
Yeah.
Every node is optimizing its connection to every other node to ensure the data flows as fast as possible.
Which makes it even harder to regulate. You can't just turn off the central server.
The intelligence is distributed across the topology.
So where does that leave us? We have a breakthrough in efficiency. We have a viable path to a truly responsive IoT.
We do. And for industries like logistics, energy grids, and healthcare, this is an absolute win. We need dual perigee or something like it to make those systems safe and reliable.
But for the average citizen walking through a smart city?
For the citizen, it means the environment becomes much more responsive, but also much more observant. The lag is gone. The invisible web